You didn't. It was good.
Wasted. No, not wasted, but like,
Okay.
that's the wrong word.
Okay, so
Yeah, if
Wrongly
we
wasted.
did
so
some
you,
last
you
time.
did do some good stuff. You guys calculated. You did some good differentiation.
So
there,
you
right?
say good, do you mean right?
Yeah.
Oh, sweet.
Yeah,
So
different.
F prime. So this is just a chain rule, right? So we've got cosecant hand is just is negative cosecant cotangent, right?
Yeah.
Okay. Times derivative of hand is 3/2. 3/2 times 2 is 3,
So
right?
negative three.
Everybody good with that?
Yeah.
So that part you did well. Right?
But when we just put hand back in there?
Yeah.
Yeah.
Okay.
Whew.
I was waiting for
Oh.
like that's where you went wrong, and then all of that was pointless.
No, that was good.
Okay.
Okay, any questions on that? Everybody okay with that?
So we bring.
And then when we multiplied by the 3/2, we just put that out front with the 2, right?
Yeah.
Okay. And change that. Good. So then this is an ugly one, right? So now we've got to do -3 times the product, right? Use product rule. So we said, you guys said cosecant, we'll do this one times the derivative of this one, how about? So cosecant hand, the derivative of cotangent is negative cosecant, right?
Yeah.
Squared. So we'll just make that a negative cosecant cubed. And, everybody with me?
Yeah.
Okay. Okay, plus cotangent times the derivative of cosecant, right? So the derivative of cosecant is cosecant, negative cosecant cotangent. So the overall sign of the term becomes negative, right? And we end up with
Cosecant cotangent squared.
cosecant, right.
Yeah.
Derivative of cosecant is cosecant times cotangent, which is being multiplied by cotangent. So cosecant cotangent squared, right? Does that make sense? Okay, once again, we were taking the derivative of the first times the second. Derivative of cosecant is cosecant negative cosecant cotangent. So cosecant cotangent times cotangent is cosecant cotangent squared. Okay? Okay, good. Well, let's go ahead and distribute the negative. How about? And just make those positives. That's one thing we can do. Okay? And now we've taken our derivatives, right? So now it's a matter of finding critical numbers. But before we do anything, we should determine where is our function defined. Meaning probably more precisely, where is it undefined, right? Because this is, and we haven't done a lot of this yet, but the table really makes this very clear. Remember that if a function is undefined at a value of x, does it make sense to even think about a critical number there? Right? Critical numbers are only useful when the critical numbers are within the domain of the function. You obviously can't have an extremum or a point of inflection where the function isn't even defined, right? So the first thing we want to do is we want to look at the domain of the function. So let's ask the question, where is this defined? Well, where is cosecant undefined? Okay, so let's skip a page here and look at what is that in terms of sine and cosine? That's how I would always do this. 1 over sine. So f of x is going to be undefined where what happens?
Sine is 0.
Where sine is 0. Okay, so let's look on our unit circle. Where is sine 0? Okay, it's at 0 and 0 and pi, right? So it's really at any multiple of pi, isn't it? Right? An infinite number of places. So it's going to be at these places on the unit circle, which in our infinite number of laps would just be described by 3x over 2, because that's theta, right? 3x over 2 cannot equal n pi, where n is just an integer, right? Does that make sense? Okay. This is a really cool way to do this. And we'll go, in hindsight, we'll look back and say, because you might be thinking, well, why don't we just say x can't equal, because x is being multiplied by something, right? The trig function is only seeing hand, or call it theta, right? It doesn't care how we build these angles. The angles are being built from this function of x, right? But sine of hand equals 0 when hand equals n pi. Does that make sense? Okay. So now we'll solve for x. So if I multiply each side through by 2/3, I get x cannot equal 2/3 n pi, right? Okay, so where's that going to be? What values of n then? Our domain is the open interval from 0 to 2 pi, right? So what values of n are going to produce, what's the word I'm looking for? Are going to produce discontinuities in our function, places where the function is undefined. Right, so we're solving for x. X is not equal to what? Well, let's just try it. If n is 0, what do we get back? So that's not in the interior interval, not in the open interval, right? What about if n is 1? Well, we'd get 2/3 pi. That works. That's between 0 and 2 pi. If n is 2, we get 4/3 pi. And if n is 3, we get 6/3 pi, which is 2 pi. And so that one we don't care about, because we're only looking, remember, on the interior interval, right, the open interval. Okay. So then what's that tell us? We can go back up here and say, okay, well, for our function, x cannot equal 2/3 pi or 4/3 pi, right? Does that make sense? Okay. So let's make our table. I'm going to make our table on this other page because we have a lot of work to do on this page. So this is so cool. Okay, so here's our open interval, which you did great. But before we even start to look for critical numbers, let's write this in. 2/3 pi, oops, and 4/3 pi are places where the function is undefined, which means vertical asymptote. How cool is that? So now we've broken up our table into 3 distinct universes, right, that are separated by these vertical asymptotes. Okay? Right? Those are important features in our graph, aren't they? Those vertical asymptotes. And they show up in our table really easily. All right, so now we'll go back and we'll find critical numbers. So let's look at our questions so far.
What was the base thing that you derived all of the logic for the unit circle?
This one?
Yeah.
Okay,
so the cosecant.
Okay, so we said that, yeah, we know that the original function is just cosecant, was it 3 cosecant?
-3 cosecant.
-3 cosecant, not that it matters, but.
Yeah.
So if it's -3 cosecant, either way, it's the bottom that we're concerned about, right, the denominator. We know that f of x is going to be undefined when sine of hand is 0. Well, sine of hand is 0 when hand is an integer multiple of pi. And hand is actually 3/2 x, and so if I solve for x, which is my variable, x values of 2/3 pi and 4/3 pi are going to make hand equal to an integer multiple of pi, right?
So what we did is we just did the same thing, but instead of using the cosecant, we used the cotangent.
No, you just didn't, you were going to waste some time, because you were going to have to go through and do this math right here to try to find critical numbers, right, for both layers of the derivative, and there's no need, right? We know that places where sine is equal to 0 on the bottom, right, the places where sine of hand equals 0 cannot produce any kind of critical number because the function isn't even defined there. They're vertical asymptotes.
But you said
right?
undefined was critical.
No, undefined derivative, right?
Oh.
But an undefined derivative only makes sense as a critical number if the function is defined there, right? So what I always tell my students then is, and this relates to the table, is that successive layers of derivatives always inherit the undefined parts of the domain, right? Does that make sense? They're going to inherit the asymptotes from the previous row. So you know, guaranteed, that if the function is undefined there, well, I just made dot, 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 because all of these functions are going to be undefined there, guaranteed. It's always that way, okay? But we want to start at the top and work our way down when it comes to that stuff, to asymptotes, right? There's no point even looking at these as being potential. Am I being clear on this? I feel like I'm not being very articulate, but these are not potential critical numbers because the function isn't defined there.
So once it's undefined, it's all the way down the table?
Yep, all the way down the table. Yeah, exactly. And that informs your thinking about how finding critical numbers, because like watch what happens with this first one. If we take, let's take this derivative right here. F prime of x equals, if I write this in terms of sines and cosines, I'm just gonna get a -3, cosecant is 1 over sine, cotangent is cosine over sine, right? So I'm gonna get a -3 cosine of 3x over 2 over sine squared 3x over 2. You see my point? When we look for critical numbers here, do we need to even look where the bottom equals 0? No, because the bottom equals 0 in the first derivative, where it equaled 0 in the original function, those aren't critical numbers. The function's already undefined there, right? So all we need to do, the only place we need to look is where the top equals 0, right? So then we could just say f prime equals 0 when cosine 3x over 2 equals 0, right?
So is that the thing that we missed?
Well, no, we
I
were
think-
right at that step when you stopped us.
Yeah, you guys are kind of there.
So we
right.
haven't hit the thing that we missed.
No, I mean, really, you didn't miss anything, it's
We
just
just did
that
it
you didn't
different,
start
taking
at the
longer.
start. You didn't start with this.
Right.
And that's a real common mistake, I think, with people that are just starting calculus, is you wanna jump in. But the first thing you always wanna do is you wanna know where is the function defined.
Haven't we always started at the derivative and not the original?
No, not really, but we haven't really done problems like this, honestly. I mean, think about what we're doing now. We're actually analyzing functions to find relevant features in the, right? So we're trying to find extrema, points of inflection, right? And so when we're in search of those things, we want to try to make our search as efficient as possible and only look in the places where it makes sense to look, right? So then we just want to know when is cosine hand equal to 0. And on the unit circle, we know that that's going to be when, on the unit circle, we know that cosine is 0 there or there, right? So that's going to be either at pi halves or 3 halves pi or 5 halves pi or et cetera, right? Okay, so what values would work for us? When does this equal 0? This equals 0 when x equals what? So we got to set
Pi and pi
3.
equals 3. We had just finished finding those out. It's pi and pi equals 3.
pi
Or
and
pi
pi,
over 3.
pi and pi over 3?
Yeah.
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 Right, that's it. Okay, and how could we do that generally speaking? What we want to say is when does 3 halves x equal, how do we say the infinite number of, how do we say all of these infinite
But we-
places on the circle at once?
We would only need just the 1 and 2.
You're right, but what if this had been, for example, let's just say this had been something like 7 halves x. Then it might get a little bit iffy, because then there's going to be a whole bunch of places, because the argument's being accelerated, right? And so as I put in value, see what I'm saying? And so, actually, is that right? We get, what if it was like 1/2 x, or 1/4 x? Then there'd be different values of x that could make, there'd be more values of x that could make that work than just those two, right? See what I'm saying? Okay, so in general, it's good to look at this generally and say, okay, let's just find out when does theta equal an odd multiple of pi halves? Because that's really what those are, aren't they? Those are the odd multiples. If we start here and we work our way around, that's pi halves, 3 halves pi, 5 halves pi, 7 halves pi. Or if I go backwards, minus 1/2 pi, minus 3 halves pi, minus 5 halves pi. It's any odd multiple of pi. Remember how we said that? How do we say an odd number?
Plus 1, n plus 1, 2n plus 1.
2n plus 1 or 2n minus 1, either
Yeah.
way, right? Usually for some reason, we say 2n minus 1. So that's any odd number, right? there's an odd multiple of pi halves. See what I'm saying? So now we could multiply each by 2, get rid of that, and just solve for x. So what do we get? We get x equals 2n minus 1 over 3 times pi. We need like 90 minutes here, don't we?
Can we continue this on Monday and have, like,
We're just going.
can we finish it?
Yeah, you